Okay, welcome to the first video for energy. We are going to first consider kinetic energy. This is something you should remember from last year. The short technical definition of entropy is that it's a number, a scalar, not a vector, and it's associated with the state of a system of objects. Energy can be changed by forces that act on the system, and the first kind of energy is kinetic energy. It's associated with motion. That's the word kinetic. The formula we use for it is 1/2 mv squared, where m is the mass of a particle, v is the speed of that particle. If you have several particles in the system, you calculate the kinetic energy of each one, and then add it up. So an example, estimate the kinetic energy of a sprinter. Well, someone who goes 100 meters in 10 seconds is moving at about 10 meters per second. And then a typical person's mass, let's say 70 kilograms. And then we calculate the kinetic energy, 1/2 70 kilograms times 10 meters per second. And we're going to get 3,500. The units are kilogram meters squared per second squared, which we call the joule. The next topic is work, or working. And when a force does work on a system, that force is transferring energy to that system. Since the only kind of energy we know about so far is kinetic, we said that the working is equal to the change in the kinetic energy. So let's try to get an expression for the working that a force does in terms of the force, rather than in terms of the kinetic energy. So let's say we've got some object initially with mass m, initially moving at speed v0, and we apply a force over a distance delta x that causes this particle to speed up to a final speed v. So we want to find out how much the kinetic energy of this increases. And so delta k is the final kinetic energy minus the initial kinetic energy, which we can write as 1/2 m v squared minus v0 squared. And that looks kind of familiar. We have an equation that has v squared minus v0 squared in it, and that's the third kinematic. What the third kinematic says is v squared minus v0 squared equals 2a delta x. And where's the acceleration of this particle coming from? Well, it's the force. Newton's second law says a equals f over m. So we'll say v squared minus v0 squared equals 2 over m times f delta x. And then we'll substitute this in here. So we have 1/2 m times 2 over m f delta x. The m's and the 1/2's cancel. And we find that the change in the kinetic energy, or the working that the amount the force works, is equal to the force times the displacement. And that is going to be our definition for work, or for the work done by a force, f delta x. But there's a catch. We assume that the force was pointing the same direction as the displacement in that example. But we know that forces are not always in the direction of the displacement, and so we need to modify that to have an angle in it. And it turns out that if we have a displacement like that, and the force at some angle to it, we call that angle phi, the expression for work in this case is, okay, let's be consistent here, that's d, not delta x anymore, is fd times the cosine of the angle between them. This is an equation you really ought to memorize, and you need to know what that angle is, because problems you'll work will have several angles, and you need to figure out which one you're going to use. If we look at this, we find that if the force points in the same direction as the displacement, the work that it does is positive. If the force points in the opposite direction from the displacement, the work that it does is negative. And if the force and the displacement are perpendicular, no work is done. That's important. But the thing is, we have this mathematical operation that comes up quite frequently, and it's called the dot product. If you have two vectors, A and B, the dot product of A and B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. So we can also write work as F dot D, which is a convenient piece of mathematical shorthand and will enable you to link this to other ideas that we come up with later. You should have heard about the dot product in your pre-calc class. Now, there's two ways of calculating the dot product. If you have magnitudes and directions, you can use the one we just developed, the product of the magnitudes times the cosine of the angle. But if your vectors are in unit vector form, it's actually very easy to get the dot product there. If you have A dot B, you can write that as the x component of A times the x component of B plus the y component of A times the y component of B plus the z component of A times the z component of B. And then if you have vectors of more than 3 dimensions, you just keep adding on. So let's say we have a sum force that equals 3I hat minus 2j hat newtons, and it acts over a displacement of, let's say, I hat plus 4j hat meters. What's the work done? Well, it's just F dot delta x, so it's 3 newtons times 1 meter plus negative 2 newtons times 4 meters. So the product of the x components, product of the y components. And so here we get 3 and negative 8, and we get negative 5 joules is the work that done by this force. Dot product. It's fun. Now, if you've got multiple forces that are acting on an object, each one might be doing work, and we have this thing called the net work, and it's the sum of the work that the individual forces do. It's pretty simple. Calculating net work is usually easier than calculating net force because work is a scalar, and adding scalars is something you learned in first grade. So here's an example. We've got a block, mass 4 kilograms, slides 3.4 meters down a frictionless plane, angled 20 degrees. Find the work done by each force, and then the block's final kinetic energy. Well, it's frictionless, so we got to identify the forces here. We have the weight of the block. We have the normal force on the block, and there's no friction, so those are the only forces. Now, the work done by gravity is equal to the force of gravity times the displacement times the cosine of an angle. And this is where it gets tricky, because new beginners at physics always want to say, oh, there's an angle there, it's 20 degrees, but that's not the angle that goes into this formula. Because gravitational force points that way. Displacement is here. This angle here is not 20 degrees, but 70 degrees. And then to get the magnitude of the gravitational force, we do 4 kilograms times g. Delta x is 3.4 meters. And cosine 70 degrees. We get a calculator. 4 times 9.8 times cosine 70. And we find that gravity does 45.6 joules of work. And notice that it's positive because gravity is pulling it down the ramp and tending to make it speed up. The work done by the normal force is 0, because if you notice, the normal force is perpendicular to the displacement, so the angle is 90 degrees and does no work. That means that the kinetic energy is delta K because these forces that do work on this system increase its energy by 45.6 joules. And since it started out with no energy, its final kinetic energy is 45.6 joules. Since we know the mass, we could also calculate its speed, but we're not going to. We could have done this with kinematics and dynamics, but in this case it was much easier to use energy. So last slide for today. Let's say you tie a weight to a string you swing it around over your head. We did a lab like this last year. The question is, how much work are you doing on the weight? To answer that question, let's draw a picture. You know that if it's moving in a circle, the force that you exert on it points to the center of the circle. Also, that's the direction the string goes. And at any given time, the displacement is perpendicular to the force. That means you do no work. Another way you could tell that you did no work, so you either say that force is perpendicular to displacement, or the speed is constant. It's changing directions, but it's not speeding up or slowing down, and so that would mean that the work done, or the net work done, is 0. And for tomorrow, I'm going to check questions 1 and 2 in Chapter 7. You should also be able to work up through problem 11.